Hello, my name is Shankar. I'm a postdoc at the University of Manchester, and I'll be talking to you about how we can best modify gravity using data from future large-scale structure surveys. So I'll start off with an introduction that hopefully gives you some idea why we should care about modified gravity in the first place as cosmologists, and also some intuition as to why general relativity needs to be tested. That will then lead on to the main challenge associated with modified gravity, which is actually describing a parameterization of modified gravity that is valid across all cosmological scales. And then I will talk to you about some of the work that I have done in collaboration with Dan Thomas and Professor Richard Batty at Manchester on n-body simulations of modified gravity and how we've computed the matter power spectrum as well as the weak lensing convergence power spectrum from these simulations and compared that to fitting functions that predict these observables. I will then move on to some results from ongoing work that will connect to how we can use data from large-scale structure surveys to forecast modified gravity as well as publish constraints on it, and will then conclude. So here are some of the issues that should keep some, if not all, cosmologists up at night. And of course, the first being the two main ingredients to the lambda CDM model, which is the current accepted model, are unknown, i.e. the underlying nature is unknown, dark matter and dark energy. And of course, this is a very well-known fact and has been the subject of active research for a long time. But in addition to this, we also have another point, which is that general relativity hasn't actually been tested over a large range of scales where it is assumed to be valid. And what do I mean by this? I have a little cartoon. We have local tests of general relativity, of which gravitational wave events have recently contributed to, like compact object mergers and so on, that have constrained gravity to be very strongly close to general relativity. On the other hand, we also have cosmological observables like the cosmic microwave background anisotropies and weak lensing and so on, that have again constrained gravity to be close to, if not identically, general relativity on very large scales as well. You have a whole host of scales in between where gravity hasn't really been tested yet because we haven't been able to model things to a sufficiently accurate level. And this is a scale that we often associate to the nonlinear regime, where the density contrast is not small. Now, this motivates the idea of modified gravity that can hopefully try and explain the effects of dark energy and dark matter naturally using the equations of motion rather than calling upon some exotic new ingredient in the cosmological model. The issue with modified gravity is that the model space is extremely vast and rich. And it turns out that it is quite difficult to come up with a parameterization that encompasses a large portion of this parameter space while simultaneously being valid on both linear as well as nonlinear cosmological scales. So the parameterizations that exist have to date been only designed and validated on linear scales where the density contrast is small and cosmological perturbation theory is valid. And so analytical constraints are possible. However, most future experiments like Euclid and Rubin and so on will generate data mostly in this regime where such parameterizations haven't really been validated. So we have this problem, and the solution to this problem, it turns out, is connected to the regime known as the Newtonian regime, where velocities as well as the gravitational potentials are both assumed to be quite small. and therefore higher order terms associated with these quantities are negligibly small. And it turns out that under this assumption, one can write down a parameterization for modified gravity, for general modified gravity models, that is valid on all cosmological scales. In other words, to derive these equations, this density contrast that you see over here need not be small. And this was shown first by Dan Thomas, who was my co-collaborator. And the other crucial thing that you need to actually know about these equations is that the first equation, which is the standard gravity Poisson equation, only depends on one parameter, which is this mu, which in GR is just set to 1, but in general modified gravity is promoted to a general function of space and time, and can be thought of as a rescaled Newton's gravitational constant that is now both time and scale dependent. And the geodesics of massive particles only depend on this equation. And so if you're interested in running n-body simulations of modified gravity, this is the only simulation you care about, and therefore this is the only parameter that you care about. The other parameter, eta, only affects photon geodesics, and we will come back to how that can be probed using our formalism. So what we've done is exactly as I've described. We have come up with n-body simulations of modified gravity where mu has been promoted to a time-dependent function. And this is, we think, a logical first step towards the full time and scale dependent analysis. A lot of the phenomenology that we will see in this time-dependent case will help us understand and inform, in fact, the analysis that is more generally time and scale dependent. And what we've done is we've divided our simulation redshift range into different redshift bins whose width is basically such that the linear growth in all of these bins is the same. And the value of mu in each of these bins is tuned such that the linear growth, the linear matter power spectrum that we measure at the end is, again, exactly the same. We have the step function like simulations where mu is switched on in one bin and then switched off in the others. And what that gives you is the ratio of a matter power spectra with respect to lambda CDM, where in this case, instead of regular lambda CDM, we're taking the ratio with respect to a rescaled lambda CDM, where the initial conditions are changed to match these modified gravity models. And you can see that on linear scales, all of these simulations have identical linear matter power spectra. And as you go from linear to nonlinear scales, you start seeing wildly different nonlinear behavior depending on when and for how long you modify mu, and of course, its value as well. And this rich phenomenology is telling you that fitting functions that predict the matter power spectrum purely based on the linear case will fail. And this brings me to our comparison of the different fitting functions that are available in the literature, and our implementation of the so-called react formalism, which is a halo model-based approach that is slightly modified, is actually significantly more successful in computing or predicting the matter power spectrum in our simulations. And what we show here is this so-called k-fail parameter, which is basically the first wave number at which the fitting function that we consider fails to predict the simulation up to an accuracy of 1%. And you can see here that React significantly outperforms its closest competitor, which is HaloFit. And we considered a few others, but none of them were actually gave us k-fails that got anywhere close to the ones that we see here. So we have this nice formalism or pipeline that has been validated against n-body simulations for specific bin modified gravity models. And we have a fitting function that can actually predict the matter power spectrum. And therefore, we have a quicker pipeline that we now are hoping to validate for a more general portion of the parameter space that encompasses, hopefully, what people are interested in testing in the future. And in fact, the Euclid mu sigma parameterization forecast paper has picked up this pipeline, and I'm leading along with a few other people, including Lucas Lambriza and Dan Thomas as well, and Noemi Frashante and a few others on forecasting modified gravity for Euclid. Now, of course, we're not only interested in the matter power spectrum, but also interested in the weak lensing convergence power spectrum. And I've shown you here how our modified gravity parameters affect the weak lensing convergence power spectrum. And here you see the appearance of both mu and eta. As I said before, eta affects photons UD6. And what that means is that we can actually use our pipeline to distinguish between modified gravity models that until now were degenerate only because we only had linear data to work with, linear scales data to work with. You see, on linear scales, we have these two sets of models that basically are on top of each other. We have four models that divide into two sets. And as you go from linear to nonlinear scales, they become, and you start to see them as four independent models in the weak lensing convergence power spectrum. In other words, the shape of the spectrum is affected on nonlinear scales in a way that breaks the degeneracy between mu and eta that exists only on linear scales. So here is immediately an example of what one can hope to achieve by pushing our modeling capabilities to smaller scales. So now I'll talk to you about some of our ongoing work. We saw that the effect of modifying mu at later times around dark energy domination actually affects the way in which the matter power spectrum is modified relative to the lambda CDM case. You can see here that there is a smooth transition from the yellow to the red as one goes from higher to lower redshift, close to dark energy domination. In other words, when you switch mu on close to dark energy domination, the effect on the matter power spectrum starts to change. And this is important because we are interested in percent level accuracy, and therefore we were wondering in our earlier paper whether there is an easy way to actually improve the accuracy of REACT. And it turns out that the concentration mass relationship that exists within REACT can be modified, in other words, rescaled. Its amplitude can be rescaled to achieve a better fit relative to our simulations. And of course, this makes sense. As you modify gravity, halos should change their masses and their characteristic radii, and therefore the concentration mass relationship should also change within the halo model. So what we've done is we've come up with a fitting function that actually consistently modifies the amplitude of the concentration mass relationship in order to maximize the k-fail in our that REACT predicts relative to our simulations. The data points are basically measured from our simulations, and the curve is the fitting function for A over A lambda CDM, where A is the amplitude of the concentration mass relationship. And we see that this sort of quadratic shape at low redshift, followed by this exponential that as you go from z equals 1 to z equals 7, is consistent across parameter space. Right? So for different values of mu, as well as different bin widths, and we parameterize that by the linear growth factor associated to the width of the bin in which mu is switched on. What this means is that one can achieve more accurate k-fails out to larger values of k, and this means that you can also predict the weak lensing convergence power spectrum more accurately out to smaller scales. And this is exactly what this plot is showing. The vanilla REACT, which is our previous implementation of REACT without the fitting function, does much worse than when you use our new version of REACT with the concentration mass fitting function implemented. And what this means is that compared to the previous dark energy survey analysis, which beyond lambda CDM analysis, which performed a cut that was purely linear, in other words, got rid of all of the nonlinear data, and thereby, as you can see in this plot, lost a lot of constraining power. You can do a lot better than that with just our vanilla React implementation, but you can also then push to a significantly larger value of L, in fact, into the region where baryons will end up dominating your cosmological constraints, as was recently published by Bose and Mancini, Spuria Mancini. So this is excellent news, and this is promising, and so we are hoping to actually publicly release this tool and do a Rubin forecast with Dan, as well as Agnes Fertain, Daniel Leonard, and other people in NSST, Dark Energy Science Collaboration. I'm also interested in trying to do K-cut cosmic shear, where we're basically performing a cut in all of our matter power spectra based on our K-fails. And there's also ideas to try and produce larger data sets quicker with hybrid n-body methods, and then train neural networks on that. And COLA can prove to be interesting in that direction. And of course, there's also halo properties that you can measure within our simulations. And there's possibly a splashback signature that is associated with these bin modified gravity models that is worth exploring that. And that brings me to the end of my talk. Thank you very much for listening, and I'm happy to take questions.